Our next talk is from Catherine Rosenfeld from the Institute for Disease Modeling.
All right, thank you all for attending this session. And I also want to thank Brian for a really excellent introduction to a lot of the relevant issues and concepts related to measles elimination. So I'm going to just skip the introduction that I provided and drill down a little bit into this question of what do we really need to be able to reach measles elimination for countries. And to do that, I want to push on this question of, do we really need 95% coverage, and are there ways that we can maybe add some fidelity to that question? Particularly because if you look at historical examples, it demonstrates that high levels of MCV coverage are neither necessary or sufficient for elimination. And this table is from a recent paper by Crowcroft et al., where if you look at countries that are eliminated or verified and eliminated, there are only 33 out of the 82 plus 21 countries, so that's around 33%, that fall in that category where they have MCV1 at that high coverage level of greater than 95%. So there are many countries that were able to fall in this elimination category at a lower level. And so I think this just speaks to the fact that, maybe modeling here can help provide better or alternative or additional performance metrics that can help drive and assess programmatic decisions. And so I'm going to speak a little bit about the model and calibration that we're doing in this space. And since this is a modeling conference, I might push a little bit more than I would at other venues. So I hope you'll enjoy that adventure. And then talk about some of the analysis and results that are coming out of this, and how we're thinking about approaching this topic and some of the results that we're seeing. And so our aim, our goal is to be able to push on scales not only of individual interventions and behaviors. So think about being able to simulate at the individual agent scale, but also be able to simulate at really large geographic scales. So push to country level simulations, multi-country level simulations. And in order to do that, we're really wanting to pare down and be very specific about what goes into our model, which is an agent-based model very similar to the one that Brian described. And the idea behind this, in some respect, is being very specific about what you need in the model, just the properties philosophy. Just take what you need and be very specific about how you're going to manage those resources on the compute that you have. Fold in the best algorithms and methods that you have, and as well as be able to pair that with languages such as Python and the ability to do, for example, compile, pushing into sort of compile time processing speeds. And we hope we can make demonstrate some capability in this space. And I hope that the example that I have here, it leaves you intrigued for more. So the particular application or scenario that we have is focused on northern Nigeria, where we have some levels of vaccine coverage and demographics from data. And the data that we're going to use for calibration has been published in previous papers. And the particular model that we have, we're going to simulate with 419 specific spatial nodes, where we've distributed almost 100 million initial agents. And the model that we have can, depending on the amount of time that you run, takes only a few minutes. Now, the data that we use to calibrate this model, we're going to focus, at least for this talk, on sort of the spatial phenomena that we can see. And this, I think, is an important point to sort of hone in on, that we're not going to simulate measles elimination in northern Nigeria specifically. We're using the data that we have to be able to build a playground, to demonstrate capability, to press on some important and interesting questions and phenomena that we see. And so the two sort of general buckets of phenomena that we're going to look at is the spatial correlation between the nodes in our model, as well as the fraction of states with cases. And we'll use a tool called BowTorch, which is a Bayesian optimization tool to be able to calibrate this model. And I'm going to spend a little bit of time just sort of showing you the calibration because I think this is interesting, and I think all of you might be interested in as well. And what I'm showing here are the three metrics that we're looking to calibrate. The two on your left are correlated to that spatial correlation metric, and the one on the right is related to the network spread. And the individual dots are what are the samples that are generated by this algorithm. You can see that they're not uniformly distributed in that space. And in fact, that space that I have mapped out here is actually the parameters that we're tuning for this example. We're looking at, in particular, how transmission is spread throughout the spatial network that was described by our northern Nigeria scenario. But one thing that you'll notice here is that I'm still keeping those three metrics separate. Often in calibration, you might combine all of the metrics that you have into a single likelihood or evaluation function. You try to optimize that, right? But here what we're going to do is we're going to keep that separate and then define what's called a Pareto front, where you're basically looking at the interplay between the different things that you might value in how your model behaves. So to take a different example, I'm giving a talk today. I could wake up early and practice, or I could sleep in and be a bit happier. And both of these, and if I practice, I'll probably give a better talk. And both of these things are very important to me, my happiness in terms of how much sleep I get, as well as the quality of the talk that I give. And I might combine that, right, to be like an overall, what may be a good metric in terms of combining my happiness and my performance on my talk is, how I feel at the end of the day. Or I can be like, well, maybe I want to keep those two separate and really look at the trade-off. And that's what the concept of the Pareto front does. And so the Pareto front that you see here is defined by these, sort of sketched out by these points. It looks a little bit strange, but what we can also do is just run a grid of simulation points to see what's actually going on here, which I'll do in this red box. And when we do that, we actually see that the Pareto front is catching a really clear ridge in the simulation space, as well as, it's being able to sort of capture where there are gradients. You could imagine, some optimization metrics sort of going down, being driven by the color of the dots, where blue is better in general. And you see in particular, there's this trade-off between the far left figure, where good quality, high value metric points tend to occur at the top of the plot versus, for example, the figure in the middle, where they tend to occur in the bottom right. And so there's some tension there between the metrics. Anyway, so the way that I used this was basically to help guide where I thought simulations were that tend to generate good quality results for these metrics when taken sort of in total. Okay, so enough about calibration. Let's go into the analysis. So the particular question that we're going to press on here is with regards to, well, how well could you maintain elimination status on the simulation that I described? And what I'm going to show here is a metric where we're just going to look at the outbreak size that results from seeding our simulation with a single infection. And each dot in this figure is a single simulation run. And we're going to take our simulation and basically fiddle with the amount of vaccine coverage increasing from left to right. And we'll start with just uniform vaccine coverage in our model. And so you can see that as you move to left from left to right, increasing the amount of vaccine coverage, the simulations tend not to produce large outbreaks. And that makes a lot of sense. And in fact, there's sort of three regions of this figure. On the left, where we see outbreaks covering the entire network sometimes. And then this sort of middle part where there's partial coverage of the network in terms of the size of the outbreaks. And then on the right, where there are no outbreaks at all. And here we see that 95% level, you don't see outbreaks spreading throughout the network. So that makes sense. Now, the thing that we can do next is actually just look at the outbreak probability that's generated by the large number of simulations that we're running, which is what I'm plotting on the bottom figure, and fit some lines to it, and then also be like, well, how much does our calibration matter? And what I'm showing on the blue plots is just taking our calibrated model and reducing the strength of the network by a factor of 10, and you see that in fact it does matter and affects some of the results as well. So, all right, sort of set up how we're thinking about the problem. I've described the model to you. Now let's push again on the analysis. So the main thing to add here, or the next obvious thing to my mind, is to add some distribution in vaccine coverage, with which Brian covered as well in terms of thinking how important that is, right? The heterogeneity in the scenario. So how can we do that? Well, there are a number of ways one might consider, but what we chose to do for this analysis was to use something that's already in the literature, which is to basically base the distribution that you want to achieve off of what's, for example, observed already. So what I have on the bottom left figure is original coverage from, I believe, IHME data for each of the nodes. And that, when you look across the entire region of northern Nigeria, has some level of vaccine coverage. But I want in my simulation to have a higher level of vaccine coverage. For example, maybe 80%, which is what I'm going to be plotting in the figures on the right. But there's some choice to be made there in terms of how you increase the level of vaccine coverage by node. And the way that this method does, which was presented by Amy Winter et al., is to have in it this factor Q, which is basically an equity factor that with a larger number is putting more emphasis on regions with initially lower levels of vaccine coverage. So lower levels of Q, you're not you're increasing vaccine for nodes that have higher levels of coverage initially, higher levels of Q. You're going to focus on the nodes with lower levels of vaccine coverage initially, and what that means is that if, for example, you look in the figure on the top right, what I'm showing are the final distributions for each of the nodes that result from various levels of Q. So low equity factor, which is the orange, you see there's a wide distribution of vaccine coverage, but for the higher level of Q, it's much more closely clustered around that target level of 80%. Okay, so we have our way of generating spatial distributions of vaccine coverage. Let's see how that affects the results that I showed you before. So what do we see? Well, we see two things that are initially confusing and unintuitive. Great, let's explore that. The first is that if you look at the orange line, as you're moving with increasing vaccine coverage from left to right, you're actually seeing that particular scenario is behaving in a much more desired way than the other models. But that scenario is our low Q scenario, our low equity scenario. And it would be nice to understand what's happening there. The other unintuitive thing that's happening is that for our high equity scenario, the purple dots, we're actually getting outbreaks at fairly high vaccine coverage of 95%. What is going on there? And the answer has to do with the spatial component of the model and how we're choosing to set the vaccine coverage, and also how we're choosing to seed the outbreak in our simulation. So what I didn't tell you before was that, yes, we're seeding our outbreak with a single infection, but we're also seeding it in a specific node. And that's the node that's highlighted here by the red dot in the southernmost part of our model. And what's important about that particular node is that it has initially a relatively high vaccine coverage compared to particularly the northern part of this model. And so what that means in practice, when you apply the algorithm that I was describing before, is that, for example, if you wanted a target coverage level of 80%, that particular node, which is indicated by the red lines and arrows, starts at a fairly high vaccine coverage, and it actually gets pushed up to an even higher level of vaccine coverage than your target level of almost 90%, when the target level is 80%. And so essentially what that's doing is it's making it very unlikely for the outbreak to proceed in that particular node, and therefore it's much less likely to spread to the rest of the simulation. Now, the other unintuitive thing that was happening was, why were there such large outbreaks for the high equity scenario? And I think the reason there is that for really high levels of coverage, you see something really sort of unintuitive happening, where for the purple dots, where for the purple lines, the purple dots, which looks like a line, you see that there are actually a lot of dots that lie below that high coverage level of 95%. And to walk back a little bit and just walk through what these figures are showing, what we're plotting is the initial vaccine coverage that's derived from the IHME data, and then the resulting vaccine coverage that comes from that scaling algorithm that I showed before. And so I think this doesn't speak to the, this isn't meant to say that that algorithm or method is wrong. I think it's a very reasonable way of going about trying to generate these distributions, which is a hard problem in itself. Rather, I use it to sort of demonstrate the fact that as we're doing this process and thinking about how important it is to be able to generate these distributions and to be able to motivate where they're coming from and have them grounded into projections and scenarios that we think might occur. Okay, well, the next thing one could consider doing is saying, well, you were seeding that specific node down in the south. What are alternative ways of starting the outbreak in your simulation? So a really one intuitive way would be to say, well, let's weight the probability of where that initial infection occurs by the number of zero-dose children who are in the node. And that's what we're showing here. And what we see is that the results that come from that scenario are now starting to match a little bit more with, I think, our intuition for how this should proceed, where our low equality scenario is now the one with the direst outlook, and we have a better performance for higher equality scenarios. Another really intuitive way to try to seed the network would be just by population, the number of people in the node. And we can do that as well. And if I flip back and forth between the two, we see that the top chart, which was the size of the outbreak, doesn't seem to change too much between those two ways of seeding, right? But if you look at the bottom chart, you see that there is a distinct change in terms of the outbreak probability, right? So our assumptions that go into something so basic as to where do we think infections are likely to happen to seed this are quite important. All right, so to conclude, I think that there is a clear need for new tools and thinking towards measles elimination, particularly with the regards to providing additional benchmarking and how models can help inform that. I think the particular example of scenario modeling and country-specific work that Brian did is also really important in this space, and they have a complementary approach that can, I think, together be quite powerful. And I hope that I've convinced you that the role of spatial modeling that can scale to covering large geographic regions has a lot of power and utility in the space, and also highlighted some of the challenges, or maybe for a half glass full person, the opportunities in this space as well. So I thank you for your attention, and I'm happy to take any questions.
Thank you very much, Catherine. Excellent talk. We have a few minutes for a couple of questions, please.
Very, very naive question. What kind of level of confidence would be required to change, elimination status or what these benchmarks and targets look like? I mean, it seems clear that the 95% number is not a magic number, right? And treating it like a magic number could be harmful, but I don't know, it seems like there's so much uncertainty about all these other parameters. There's no other number that would be more certain? So I'm curious what kind of evidence would convince you of what a better number would be, or should it be different for every context? Or I don't know. I'm kind of curious how you connect to this with what the recommendation at the end will look like, or you know, how would you know you had gotten there?
Yeah. So I don't think of it necessarily as, you know, what should the recommendation look like and how do we know when we have it, but rather how can we have a conversation about what are other important things to think about, to have conversations about, and where we could also think about building up capability with regards to surveillance and other modeling efforts. So that's sort of more the trajectory of where I see this work going, not being like, what are the numbers that you need in the end, but sort of how do you build up that conversation in terms of, you know, thinking about the problem in maybe a slightly different way. Does that help? Yeah. Because I think that's a very good point.
Okay, this is question / comment / opportunities for the half full person, the glass half full person. I wonder about the point you made about how you define inequality is really well taken. And I wonder about our health system and how that creates or doesn't create that inequality. And like, I could see an argument for in Lagos in the South, right? It's really easy to get to 90%, but then that last 10% is really, really hard, right? And so how do we think about sort of the structure of the system and those who are likely to be left behind, and the role of campaigns and sort of closing that or not? So anyway, like an invitation to a complicated conversation, I guess, is my comment. If you have any thoughts about how we do that better.
Yeah, I think this is an area where the conversation really has to happen. And in some sense, you know, there's like, you could think about sort of parameterizing your like particular area's trajectory in that space. But to be honest, I don't view myself as an expert in that region. I think that there are other people who know a lot more about that in this room. And that's where we really need to, I think, have conversations and pull in other perspectives there.
All right. Thank you very much, Catherine. Excellent talk.